Hey everybody, we have this mouthful of words problem that wants to know how many multiples of 14 uh, that divide 14 factorial have exactly 14 divisors. So it's a lot of 14s floating around here. Let's talk about the prime factorization, which is pretty clearly important right here. We can use the floor function to actually compute the highest power of each of these prime factors. So in this particular case, I'll just do it for 2. I'm not going to do the whole thing. But a lot of these people that do these contest problems, designing and solving, just write down the prime factorization. But this would be difficult. Think about doing 14 factorial, however you can, and then doing a prime factor tree. That would be a nightmare and you wouldn't get it right. So this is a shortcut way of doing it. And what you do is you successively divide 14 by powers of 2 until you get a floor of 0. Okay, and so what's going to happen here, and this is kind of a cool little thing here it's a mouthful of words, like I said, but so we'll put 2 squared here, okay, and then we're going to go out to, I think we need to go out to 2 cubed. 2 to the 4th would leave a floor of 0. 2 to the 4th is 16. So we can do this 14 over 2 cubed. And I'll try to explain this to you in a way that I think I understand. Okay, we can stop right here again because 2 to the 4th is 16 and the floor of 14 over 16 is 0. Okay, now what this gets you right here, this very first one would get you what, 7? 14 over 2 is 7, and the floor of an integer is an integer. Now this is 14 over 4, which is 3 and something, right? So this would give you 3. Okay, so the floor of 14 over 2 is 7. The floor of 14 over 2 squared is 3. And the floor of 14 over 2 cubed, 14 over 8 isn't even to 2, right? So the floor of that is 1. So you see, notice that these objects here, these numbers, they sum to 11. And guess what? That's the exponent that you see right here, okay? Now, I'll explain this to you the way I understand it. 14 over 2 counts the multiples of 2 less than or equal to 14, right? And so there's 7 of them. But included in those 7 would be 2 squared, which has a 2 that didn't get, which has a factor of 2 that did not get counted here. Also, 2 cubed has a factor of 2 that did not get counted here. You see? So that's why you have to keep doing this, because this counts all the multiples, but some of the multiples have more than one factor of 2, namely 2 raised to the n, okay? So that's where this 11 comes from, and in a similar fashion, you could get 5 for 3 and 2 for 5 and so on, okay? So it turns out to be an important fact because divisors can be read off of this, by decreasing exponents. You can just literally enumeratively get all the divisors, although you don't have to know all of them. Now, state an obvious fact here. 14 is almost prime itself. It's 2 times 7, which makes this problem easier than the one that Adam Bertelli published. His was 12, and there was more possibilities right here. But so all this stuff I'm saying, you can read it yourself. It makes sense, right? Any multiple of 14, which is a divisor of 14 factorial, would have to be at least include this. It could include other prime factors possibly, but would have to at least look like 2 to the m times 7 to the n, where m and n are positive integers. And notice they have to be, it couldn't be 0 here because you would miss out. 2 to the 0 is 1, right? So you wouldn't get a multiple of 14. This is guaranteed to create a multiple of 14. Okay. Now, so next thing is there's a result. This is the number of divisors result here. And if you have P and Q prime, I should write that down, P, Q, both prime. They're very common letters to represent primes. But if P and Q are prime numbers, you can count the divisors easily without actually physically enumerating them, listing them, okay? By just inking the exponent by 1. You see, add 1 to 1, you get 2. Add 1 to 6, you get 7. You get 14 divisors. So this is the only way one of these objects can have 14 divisors if these exponents have this favorable property. And you guys, you can verify this. The reason why you have to add 1 is if you made one of the prime factors have an exponent of 0, that would correspond to a factor. Everything that was left over would be a factor of 14 factorial. Okay, so that's why you ink this. And again, if you want to see an example, let's just do a quick example. D at let's say 20, the number of divisors of 20. Okay, if you look at the, and you guys could be listing the prime factors if you want, but this is equal to D at what, 2 squared times 5? This is just an example, not related to the problem. All right, and so anyway, this would be equal to 3. There's an implied 1 there. Okay, this would be equal to 3 times 2 divisors. So there's 6 divisors of 20. You can list them: 1 and 20, 2 and 10, 4 and 5, right? Isn't that 6 already? So that's 3 times, oh, I'm sorry, 3 times 2. Erase that. Okay, so you get 3 times 2 right here, which is equal to 6. So there's 6 divisors. And again, you can say them in your head. 1 times 20, 2 times 10, and 4 times 5 give you the 6 divisors. Okay? But anyway, we wrote this down because it's important to impose all, there's 3 conditions, right? You have to be a divisor of 14 factorial. You have to be a multiple of 14, and the divisor itself must have exactly 14 divisors. So 14's magic here, right? So the only one that really fits here is 7 to the 1st times 2 to the 6th. See, that's guaranteed to be a multiple, right? That would be equal to 14 times 2 to the 5th, right? 14 times 2 to the 5th is 14 times 32, whatever that is. You don't need to know that. But that's definitely a divisor of 14 factorial, right? This is a divisor of 14 factorial. And that's simply because you got enough 7s and enough 2s to go around, right? You have 7 squared here, and then you have plenty of 2s to go around, which is always the case on these factorials, right? But you can't use any of these other prime factors because it wouldn't fit with this result here that you need one of the exponents to be 1 and the other exponent to be 6. You know what I mean? You're going to always have to have 2 carrying the 6 here. Otherwise, it wouldn't be a factor of 14 factorial because there's only, what, 3 has 5, 5 has 2 exponents, 7. And so you see the exponents aren't big enough to give us any more divisors of 14 factorial with the condition that they have 14 divisors themselves. So this is the only answer, ladies and gentlemen. Unless I made a mistake, let me know. This is the only, there's only one. So the answer to the question is 1. There's only 1, and that would be 7 times 2 to the 6th. 7 times 2 to the 6th. And again, that's why, this is the answer to the question. But the one divisor with the property, see, again, this number, 7 times, that's 7 times 64, right? 7 times 64, whatever that is, 448. But it has 14 divisors, and it is a divisor of 14 factorial by form alone, right? Here's a 7 right here, and then you can pluck out 6 of these 11s, right? And whatever's left over will be the divisor pair combination that you would get. But anyway, folks, the answer is 1. Hope you enjoyed that. I like the part about using the floor function, to count, to figure out your prime, your canonical prime factorizations. A lot of the competitors in these competitions, they'll just write this down. I don't know how they do it so fast. Really, they really can't. If you think about 14 factorial, it's uncomputable in your head. Even if you used a calculator, you'd have to, all these things are divisible by 2, but then you got to just work your way along. So this is an indispensable tool in terms of finding the prime factorization of a factorial expression. And notice we just found it for 11. You'd have to go through the same thing, but it's easier with 3 to the 5th because the exponents are smaller and you don't have to go all the way out. Okay. But anyway, thank you for viewing. Hope you enjoyed.